Welcome once again to our YouTube channel. Thanks for subscribing to our channel. We really appreciate you. It's nice that you've been coming along with us. Today we quickly want to look at the NECO 2024 chemistry practical. The quantitative analysis or the titration aspect specifically. That is what we want to look at today. So I will encourage you to try as much as possible to come along with us like you have always done, and you get to learn as much as possible from this tutorial session. Let me quickly thank those of us that have been subscribing to our channel. We really appreciate you. For those of us that are yet to subscribe to the channel, please don't fail to do so. Subscribe so you get the best out of this channel. Thank you. Alright, so diving straight to what we have today, we want to talk about the NECO 2024 chemistry practical, particularly the quantitative analysis or the titration. That is what we want to talk about today. So that is what we will be looking at. So we have the NECO 2024 chemistry practical. So that is what we want to look at, particularly the quantitative or the titration, the quantitative analysis or titration. That is what we want to look at today. Now, like I said, NECO has given us the specimen that will be used for this year's practical questions or practical examination, and we are going to be using that in the course of our practical, particularly for this session. Now, after we must have carried out the titration, we will then look at some possible sample questions that can help to guide our thoughts, questions that can help to shape our mind and prepare us adequately for the practical examination. So like I said, we were given an acid-base titration this year. An acid-base titration. Acid-base titration, that is what we were given. Acid-base titration. And what are the parameters that we were given? We were told to use, for our acid, we were told to use the H₂SO₄. That is what we were told to use for our acid, where we were given a particular concentration to prepare the specimen. So for our acid, we were told to use H₂SO₄, and for the base, we will be using sodium thiocarbonate. Sodium thiocarbonate. So those are the things that we will be using in the course of this practical session. So we have this prepared. We have the acid prepared here. We have the acid prepared, and also we have the base prepared for this particular session. So like I said, we'll be making use of those for our practical. Now, the kind of indicator that we will be using for this acid-base titration, since we are working on a strong acid and a weak base, the suitable type of indicator that we will be using for this titration is going to be the methyl. We will be using the methyl orange. That is going to be our indicator. That is what we will be using for this particular titration. So you follow me now where we quickly carry out the titration and show us the steps are required and then how we go about it all. So let me just put this here so we'll be able to see all that is being done. So I have my return stand here already clamping my burette. So I will go ahead with my practical right now. So this is what I do first. I am going to put my acid into my burette. So that is the first thing I will be doing. So all of these apparatus have been cleansed before now. So I am putting my acid into my burette. Right, always remember to remove your funnel when you fill your burette, because drops from the content of your funnel can add to the amount of substance that you are releasing into the conical flask. So I am trying to zero my funnel right now and I have achieved that. So I have my acid here. So I go straight now to get my base. I'm putting my base into my beaker. Adding my base into my beaker. So I have my base here now. So I'm going to carry out this titration using that. So let me pipette. I'm pipetting. I'm using a 25 centimeter cube pipette to take a measurement of my base into my conical flask. Alright, so let's see. I'm trying to make it accurate, sitting directly on the meniscus. So I have that right now, and I'm going to empty into my clean conical flask. So we can see the pipette that I'm using is a 25 centimeter cube. You can see it here. It's a 25 centimeter cube pipette. So I have emptied the content of my pipette into my conical flask now. So I will add 2 drops of methyl orange. Now this is my methyl orange prepared, so I will add 2 drops of it into my substance here. So 2 drops here. So we see it. I've added, you can see it was initially transparent or clear. Now we can see the color change in it. You can see the color of the content of the conical flask right now. Now I will start running my acid into the content of the conical flask. So that is what I'm doing right now. So I'm looking for the earliest color change. I'm waiting for the earliest color change, and that is what I'm looking for. So it is always good to have a white style under your return stand or your return stand to make it possible for you to see the color change. So right now, okay, this is what I have. I have a color change already, but I can still see some traces of golden yellow in it. So let me add a little more, because after stirring, I'm still seeing that there's still slight golden yellow in it. So let me add a little quantity of this. Okay, this is where I am now. You can see the content as opposing to what we had previously before we started the practical. You can see it. So we have a color change now, changing from orange yellow to pink color. So this brings us to the end of this particular titration. So we check to see the concentration. So what we are having here is we are having 20.6. 20.6 is what we are having here. So let me quickly prepare my table, and you come up, you see what the table will look like. So let's prepare our table now. We are having something that looks like this. Alright, here I am having my final reading. Here I'm having my initial reading, and here I'm having volume of acid used. So here I'm having my rough. Here I'm having my first reading. What was it? Here I am having my first reading, here I am having my second reading, and here I am having my third reading. So that is what my table is going to look like. So from what we just did now in our burette, it was initially at 0.00, and what I am having now, like I said earlier, I am having 20.60. That is what we are having there. So let me add to the content of my burette. I want to bring it back to 0 to make the calculation effortless. So I am going to add to the content of my burette now. I'm taking it back to 0. Right, so I will zero it again. Alright, I've zeroed it again. So I am going to measure content of my base again. So we can see I'm trying to zero it to make it sit right on the meniscus. Alright, so I have it there now. So I'm emptying it into this. After which I am going to add my indicator to it. Alright, it is all done. So let me add my indicator to it. 2 drops again. And yes, that's the second drop. So we can see, look at the color change. You can see the previous color, we can see how the color is golden yellow, and we can see the end reaction. So let's see what this one turns out to be again. You can see the color change. This one is still showing some signs of golden yellow in it, but we are looking for the earliest color change. So since it has changed out of, we are seeing the pink coloration in it, so we can leave it at this. So what we are having right now, okay, we are having 19.4. We are having 19.4 now. So let's record it. 0.00, we are having 19.40. Always make sure that you leave it to 2 decimal places like this. Alright, so let me dispose this. So we take another 2 concordant readings. So let me clean very well with distilled water so we don't have any form of reaction with our materials. So I am going to take another pipette reading base. And there it is. You can see. Alright, so it is sitting right on it now. So we go ahead to dispense into our clinical flask while I add or make this back up to 0 mark. Alright, so you don't forget to zero it. So for the sake of those that are watching, let me bring this burette up so you can actually see how the reaction is done, how the reaction comes about. Alright, so my pipette is empty now. The content is in my conical flask already. So the next thing to do is to add 2 drops of my indicator. And I'm doing that now, 1 and 2. So I've added the 2 drops. You can see the coloration. You can see it. So now we can watch how the color change happens. You can see it. Gently I add the content of my burette into my conical flask while I stir. And as I do that, the content of the burette is running into the conical flask, carrying out the neutralization reaction as supposed. So the more I stir, the more the color changes and the color disappears again. Then we are having it looking like this. And now we have this color change. You can see the color change that we are having right about now. You can see the color change. So we see it now. It's right now at 19.6. We see it. So that that is what we are having there. So our second reading, we have it to be 19.60. Alright, so let's take one more reading to have 3 concordant readings from which we can now pick the ones that we'll be using to calculate our average titre value. Alright, let me measure my burette content again. You can see, so it is now empty. Drain my conical flask and then I empty the content into the conical flask. So I've emptied the content of my burette, of my pipette rather, into the conical flask. So adding drops of my methyl orange into it now. I've done that. So we have the coloration here already. So it is this methyl orange that brings about the reaction, making it possible for us to see. So that is the essence of the indicator. It makes the neutralization reaction, the end point, very visible. So we can see as I'm running my acid into the conical flask and shaking the conical flask, all the content of the conical flask is gradually changing in color. So we can see it. Alright, so this is what we are having right now. You can see the color change. You can see what we are having there. So what we are having here right now, we are having 19.40 again. Since we had that previously, yes, we had 19.40. So that's what we are having again. 19.40. That is what we are having there again. So when we calculate all of this now, we use this to find our average titre value. So let me put this aside so we understand how it is being done. Right, so we have this here, 20.60, very far. This one here is giving us 19.40. This one is giving us 19.60. This one is giving us 19.40. So since we have these ones here, this one is farther away from these ones here, but these ones here, they all have the difference of 0.2. This one to this one is 0.2. This one to this one is 0.2. So we can make use of the 3 of them to calculate our average titre value. And so this is how we do it. Average titre value equals, we have 19.40 plus 19.40 plus 19.40. So what we are having is, okay, all divided by 3. So when we calculate all of this now, it's giving us, we have 58.40 divided by 3. So 58.40 divided by 3 is going to give us, we are having 19.466 thereabouts. So making it let's make it a round figure. So we'll be having 19 points. If you make it 3 decimal places, so our average titre value is going to be 19.47. That is our average titre value. So that is how we get the average titre value from the table that has been produced. So for the reaction, if you want to find out the equation for the reaction, what we'll be having is going to look like this. We have H₂SO₄ plus sodium triisocarbonate. The salt, this is a neutralization reaction, acid-base titration. So we have acid reacting with the base to give us, we have sodium tetraoxosulfate plus we have carbon dioxide and then water. So that is From now we can actually look at, we can try to get out the equation for the reaction, and this is what it is going to look like. It is a neutralization reaction, so we have our acid to be H₂SO₄. H₂SO₄ plus the sodium trioxocarbonate to give us the sodium tetraoxosulfate plus carbon dioxide plus water. So that is what our reaction is going to look like. And if you look at it now, it is in ratio 1:1. This one here is in ratio 1, and this one also is in ratio 1. So basically that is what the titration is looking like. So now that we have done all of this, we can now make use of values like this as our average titral value or volume of acid used in solving questions. So we have designed some sample questions that we'll be using as tutorial questions in tackling what questions you can come across in these practical exams, particularly concerning the titration. So I will plead with you to stay glued to us as we bring that across to us right about now. Alright, so welcome back. Now we'll quickly be looking at some sample questions that we'll be using as tutorial for this particular quantitative analysis that we have just talked about. We have just done the practical, so let us tackle a few questions that we'll be using. But before we go into doing that, let us quickly see some very important formulas that we must memorize, that we need to memorize, that will come handy for us when we start carrying out calculations in this particular aspect of the practical exam. Now these are the formulas like they have been listed, useful formulas in volumetric or quantitative analysis. Now the first one there says mass concentration. Mass concentration is calculated using the molar concentration multiplied by the molar mass. When we need mass concentration, it is the molar concentration times the molar mass. While molar concentration, like you can see from this particular first formula here, we can also get out our molar concentration, which is going to be the mass concentration divided by molar mass. If we also need the molar mass, it can be gotten. It is going to be mass concentration divided by the molar concentration. And number 3 there talks about concentration, which is going to be mole divided by volume, and it is going to be in dm cube. We have this particular fourth formula here. It is very important. We need to know it. That is CAVA divided by CBVB, which is equal to Na over Nb. Ca being the concentration of the acid, Va the volume of the acid, divided by concentration of the base times the volume of the base, equals the number of moles of acid divided by the number of moles of base. That is the fourth formula here. And fifth formula there says percentage purity, when we are asked to calculate the percentage purity of a particular substance. So we make use of the mass concentration of the pure substance divided by the mass concentration of the impure substance multiplied by 100. Since it is working on percentage, so it is going to be multiplied by 100. And when we look at the sixth formula here, getting the percentage impurity, so when we must have calculated the percentage purity, we just subtract whatever we get as our percentage purity from 100. That will give us our percentage impurity. And number 7 there talks about solubility of sodium triisobicarbonate, which is the base that we are using in this particular titration or quantitative analysis. Solubility of our sodium triisobicarbonate in moles per dm cube can also be calculated using C1V1 equals C2V2. And when we are doing this, we will find out that our C1 is the concentration at the beginning of the titration. So we have our C1 to be unknown, while the V1 is the first volume that we have. Our C2 is the concentration of the base, which is gotten from the question. It is usually seen in the question, while the V2 is the second volume, or it is found in 100 centimeter cube when it is being diluted. So that is about the C1, V1, C2, V2. And we have our dilution principle formula, which is what we have just talked about, C1V1, which is equal to C2V2. And then when we look at the number 9th formula here, we have mass of salt formed. The mass of salt formed from the reaction. Remember, this is a type of neutralization reaction, acid reacting with base, so it produces salt and water. So the mass of salt formed is calculated using Cb multiplied by the volume of the base Now the volume given in dm cube, not the VB by directly, but the volume that is given in dm cube, and it is multiplied by the molar mass of the salt that is formed. And then the 10th formula here, we have it to be volume of gas at STP. Volume of gas at STP equals Cb times the coefficient of the carbon dioxide. Volume of gas produced. Remember when we look at the titration, the reaction for the titration is going to be H₂SO₄ reacting with sodium trisulcarbonate to give us sodium tetrasulfate, and then carbon dioxide is being released alongside water. So the volume of the gas, which is the carbon dioxide that is produced at STP, we have Cb multiplied by the coefficient of the carbon dioxide times the volume given in dm cube, not of B, and then it is multiplied by the volume of the gas, that is 22.4 dm cube. All of these are some of the useful formulas that we need to familiarize ourselves with in the course of this particular aspect of the practical, which is the calculation. And then we go to look at this ones here, indicators and their colors in solution. Now the reason why I'm doing this is because there's a particular aspect of these practical questions, which is number 3. It is actually practical, but it comes in form of theoretical questions. So these are some things that can come around, or that can come across, you can come across in number 3. So they could ask you the color of a particular indicator, or the types of indicator that you can list them, and so all of those. So that is the essence of bringing this to our knowledge. So we have so many types of indicators, as you can see, but I will just make mention of a few of them and their color in solutions. If I had to make mention of different indicators, we have methyl orange, we have methyl red, we have phenolphthalein, we have bromotimol blue, so many of them, but we'll just limit ourselves to these ones here. Now when we have methyl orange in acid usually is pink in color, and when we have methyl orange in base gives a yellow color, while methyl orange at the end point of a reaction or at neutral point is orange. And then if you look at the phenolphthalein in acid is colorless, when in base it is pink, and when it is found at end point or at neutral point in a reaction, it appears to be colorless also. And bromotimol blue in acid is yellow. When it is found in base, bromotimol blue appears to be blue, and then when bromotimol blue reaches an end point or a neutral reaction, it appears to be green. So these are some color changes of some known indicators in different pH concentrations. And then we have this last one here, where I am talking about types of indicators that are used for different types of reactions. Now you pick your indicator based on the type of reaction that you want to work on. The type of reaction you are working on, or the type of materials that you are using, the type of substances that is making up your reaction, will inform or will dictate, will direct the type of indicator that you will use for that reaction. And so we are having this for strong acid. We can see that strong acid reacting with strong base, the type of indicator that is used in this particular type of reaction can be any of the indicators that we have mentioned above. It could be bromotimol blue, it could be methyl orange, it could be phenolphthalein, it could be methyl red, any one. They are all suitable for such reactions. But when we have strong acid reacting with weak base, the best indicator for such reaction is going to be the methyl orange. And if we have a weak acid reacting with a strong base, we will be needing phenolphthalein to help us bring about completion of such reaction. But when we have a weak acid reacting with a weak base, there is actually no suitable indicator for this particular type of reaction, because such reaction is very vulnerable. So any indicator might, in fact, we may not even be able to get a reasonable endpoint from such reaction. So these are some indicators that can help us achieve good results in our titration. So having talked about this, let us go to explaining some questions. We'll quickly look at some questions for this particular session. Now I'm looking at this here. This is going to be our number 1 question. Our number 1 question there says A is a solution containing 4.9 grams per dm cube, and B is a solution containing X gram per dm cube of sodium trisulcarbonate. A. Put A into the burette and titrate with 25 or 20 centimeter cube of B using methyl orange as an indicator. Tabulate your burette reading and calculate the average volume of acid used. Now that is the question. Then here we have B. From your results and the information provided above, calculate the A1 concentration of A in moles per dm cube. Roman numeral 2 concentration of B in moles per dm cube. C, or Roman numeral 3 rather, mass of salt formed when 500 centimeter cube of B is completely neutralized by A. And then Roman numeral 4, we have volume of carbon dioxide liberated in B Roman numeral 3 above. So for that particular, for this fourth reaction here, for fourth question there, we are given additional information. It says 1 mole of gas occupies 22.4 dm cube at STP, and we are to assume our titre value to be 20.55 centimeter cube. So let's assume that after our tabulation and everything, after calculating our burette reading, we calculated and we arrived at our average titre value being 20.55 centimeter cube. So that is what we are going to be using in calculating this particular question. But before we go to that, let us quickly see a few things. So let us quickly write these informations out, because it will be very, very helpful. Now we have our sample A. Sample A, which is our acid. Our acid is H₂SO₄. H₂SO₄. So let us calculate the molar mass of A. So we need some informations. Our hydrogen is 1. We have carbon to be 12. We have oxygen to be 16. We have sulfur. We have sulfur to be 32. We also have sodium to be 23. All of these will be needing for calculating the molar mass. So the molar mass now, the molar mass of our A, that is of our acid, that is H₂SO₄. So let us quickly calculate that. We have 1 times 2, because our hydrogen is 1 times 2, plus our S is 32, plus our oxygen, which is 16, and it is in 4 places. So that is what we have. So 1 plus 32 plus 16 times 4 is 64. So we have everything amounting to 98 grams. So that is this is going to be the molar mass of our acid H₂SO₄. So let us do that of sample B. Sample B, and that is our base. Our sample B is our base. It is sodium thiazocarbonate. Sodium thiazocarbonate. So the molar mass now, the molar mass of B, which is our sodium thiazocarbonate, we have our sodium, which is 23, is in 2 places. It's we have 2 moles of sodium there. So sodium is 23 times 2, plus our carbon is 12, plus our oxygen, which is 16, and it is in 3 places. So we have 23 times 2, which is going to give us 46, plus 12 plus 16 times 3 is giving us 48, and that is amounting to 106 grams. Yes, when we look at it, 46 plus 12 plus 48 is giving us 106. So that is about that. Now let us quickly write out the equation for the reaction. The equation for the reaction, we have H₂SO₄, H₂SO₄ plus sodium thiazocarbonate. We have sodium thiazocarbonate to give us sodium tetraosulfate plus carbon dioxide and then water. It is a neutralization reaction. So if we look at it now, we discover that our equation is in ratio 1:1. We can see it that our reaction there, we have our substances. The H₂SO₄ is in ratio 1 and our sodium triisocarbonate also is in ratio 1. So we have our acid to our base in ratio 1:1. So having this knowledge now, having this as our foundation, we can now move ahead into tackling the questions that we have before us. So the question we have there, like we have read earlier on, A is a solution of H₂SO₄ and all of those, we have information there. So let us go straight into tackling it. Now, we start with this. Question 1. Question 1. Right. So we have the mass concentration of A from the question. Mass concentration of A, we have it to be 4.9 grams per dm cube. We don't know that of B. We don't know the mass concentration of B, but we have the VB now. The VB, we have it to be 25 centimeter cube. I remember that our volume of acid from the question there, we said it is 20.55 centimeter cube. So let us go straight into answering the first question. Question 1. So question 1 there says concentration of A in moles per dm cube. Concentration of A in moles per dm cube. That is the first one I want to answer. So concentration of A in moles per dm cube, this is the formula that we will be using. Ca equals the mass concentration of A divided by, mass concentration of A is going to be grams per dm cube, and it is going to be divided by, we have it divided by the molar mass. The molar mass of A, which is in grams per mole. So that is the formula that we will be using. So we'll be having our Ca to be 4.9, because that is our mass concentration from the question, 4.9 divided by 98. Remember, we calculated that some minutes ago. Divided by 98. So we have our Ca to equal 0.05, but try as much as possible to always leave your answers in 3 significant figures. So leaving this in 3 significant figures is going to give us 0.0500 moles per dm cube. So this is our answer for this particular question. Let me put this here so we don't get lost. So 3 significant figures. So our answer is 0.0500 moles per dm cube. That is for question 1. Let's take question 2. Question 2 is asking us for the concentration of B in moles per dm cube. You can see the question here. So we have done question 1, which is concentration of A in moles per dm cube. The second one now is concentration of B in moles per dm cube. That's the one we want to take right now. So concentration of B in moles per dm cube. In moles per dm cube. So this is the formula we'll be using. Let's use this formula. we have CAVA over CBVB equals NA over NB. So from here now, let's make a straight line equation. So we have CAVANB equals CBVBNA. Now we are looking for the concentration of B in moles per DMQ. This is what we are looking for here. This is the one we are looking for here. So it is also found here. So let us make that subject of the formula now. So we have our CB equals everything that we have here, CAVANB, all divided by, they are all divided by the coefficient of CB here, which is VBNA. So that is what we are having there. So if we go through that, we'll be having our concentration of A that we just calculated. We have 0.0500 multiplied by our volume of acid, which was given in the question. You can see it here. It is given in the question to be 20.55. You can see it right here, 20.55 centimeter cube. So that is what we are using as our VA. So we have 20.55 times the number of moles of base, which is 1, from our reaction that we wrote earlier on, the reaction for the equation, reaction for the equation rather, equation for the reaction. We have the acid to the base to be ratio 1:1. So all of that is going to be divided by the volume of base, which is 25. That is the size of our pipette, 25 centimeter cube, times the number of moles of acid, which is 1. So when we do the calculation, when we carry out the calculation, we'll be having our CB equals 1.0275 divided 1.025 divided by 25. We have 0.0500 times 20.55 times 1, giving us 1.0275, then divided by 25. So we are having 0.0411, and then to 3 significant figures, to 3 SF, we are having it to be 0.0411 moles. Remember, we are calculating this to be in moles per dm cube. So that is the answer to question 2. So question 3 then says mass of salt formed when 500 centimeter cube of B is completely neutralized by A. So let's see that. 3 now. We have mass of salt formed. Mass of salt formed when 500 centimeter cube of B is neutralized by A. That is what we have there. So the reaction there, we have H2, we have written that reaction before, but let me just write it again. H₂SO₄ plus sodium triisocarbonate, giving us sodium tetraisosulfate plus carbon dioxide and then water. So from there we have our salt formed in the above equation. The salt formed is this. The salt that is formed is this one here. That is the sodium tetraisosulfate. So the molar mass of sodium tetraisosulfate now, molar mass of sodium tetraisosulfate, we have it calculated thus. We have sodium to be 23/2 plus our sulfur is 32 plus our oxygen, which is 16 times 4. So 23 times 2 is going to give us 46 plus 32 plus 64. So we have all of these amounting to 142 grams per mole. That is the molar mass of our sodium tetrazosulfate. So the formula to use for this now, we are using mass of salt formed equals the molar mass of salt times the concentration of base times the volume in dm cube. That is what we are using. So when you look at that now, the mass of our salt formed is going to be, we have it to be 142, which is our molar mass of the salt. 142 times the concentration of our B is 0, that was what we just calculated, 0.0, concentration of B in moles per dm cube, 0.0411 times the volume in dm cube, we have it to be 500 divided by 1000. So if you look at that now, what we'll be having is going to look like this: 142 times 0.0411 times 500 divided by 1000 is going to give us 0.5, and that is going to give us 2.9181, and then to three significant figures we are having it to be 2.92 grams. So the mass of our salt formed, the mass of sodium tetrazosulfate formed is 2.92 grams. So let's go to the next question now, which is going to be Roman numeral 4. The question there says the volume, calculate volume of carbon dioxide liberated in B3 above. B3 that we have just calculated, that is the mass of the salt. So we want to know the volume of the carbon dioxide that is liberated in that reaction. So this is how we go about that. 4. So volume of carbon dioxide liberated is what we want to calculate. Volume of the carbon dioxide liberated in B3. So this is what we do. This is going to be the formula we'll be using. Volume of the CO2 liberated. We are going to be having the concentration in dm cube, concentration in moles per dm cube, multiplied by the volume in dm cube. Volume in dm cube. This particular concentration here is in moles per dm cube, while this one is the volume in dm cube, the volume of the base that we are calculating. Now we are now having the last one there to be the molar volume of the gas multiplied by the molar volume of the gas. So this is the formula that we'll be using for this particular reaction. So we have it looking like this: the volume of the carbon dioxide liberated now to be 0, we have 0.0411 multiplied by 0.5 multiplied by 0.5 multiplied by 22.4 dm cube, which is the molar volume of a gas. So we have that to look this way: volume of carbon dioxide liberated now equals 0.46032. So to three significant figure now, we are having it to be 0.460 dm cube. So that is the volume of gas, or the volume of the carbon dioxide that is liberated. So that is the answer for that question 1. So I believe we understand that now. So let us move straight to question 2 now. Question 2 there says A is a solution containing 0.0396 moles per dm cube of tetraoxosulfate 6 acid solution, and B was prepared by diluting 150 centimeter cube of a saturated solution of sodium thiocarbonate at room temperature. So we have to put A into the burette and titrate with 25 or 20 centimeter cube of B using methyl orange as indicator, and then we tabulate our reading. So like we have done previously, we are going to be using a particular reading for this question. We'll be using a particular average tetra value. So what we are using there is going to be 21.7 centimeter cube. So that is estimated average tetra value that we'll be using for this reaction. So let's continue now. From your results and the information provided above, calculate the 1. Concentration of B in moles per dm cube. 2. Solubility of sodium thiocarbonate in moles per dm cube. 3. Mass of salt formed when 500 centimeter cube of B is completely neutralized by A, the acid. And then Roman numeral 4, the volume of carbon dioxide at STP that would be liberated from 1 dm cube of B. So these are the questions. So let's go right ahead. Question 2. Question 2. So we are using 21.7 centimeter cube as our average tetra value. So let us just quickly write out a few things from our question. So from the question, we have the molar concentration. The molar concentration of A, we have it to be 0.0396 moles per dm cube. So we have that information from our question. So when we want to calculate the first question there, looking at the concentration of B in moles per dm cube. Concentration of B in moles per dm cube. What we'll be having, we'll be using this formula. We have CAVA over CBVB over CBVB equals NA over NB. So from here now we can have a straight line equation which is going to look like this. CAVANB equals CBVB NA. So we have this now. Since we are looking for the concentration of B in moles per dm cube, so we make B. We make this one here subject of the formula, and so we'll be having CB equals CAVANB all divided by, we have it divided by the coefficient of CB here, which is VBNA. And so that is going to give us our CA from the question. We have our CA to be 0.0396 multiplied by our average tetra value, which is 21. The volume, this VA here is our estimated tetra value, our average tetra value. So we are using 21.70 multiplied by the number of moles of the base. Number of moles of base is 1, all divided by the volume of base. The volume of base that we have used is 25 centimeter cube. That is the size of our pipette, and multiplied by 1, which is the number of moles of acid. So calculating this now is going to give us, we are having 0.85932 divided by 25. So we'll be having our CB to equal 0.0343 So these to three significant figures now. To three significant figures, we'll be having it to be 0.0343 0.0344 moles. The unit is very important. We have it to be 0.0344 moles per dm cube. So that is the concentration of B in question 2. So let's move to the next question. The next question there is talking about solubility of sodium triisocarbonate in moles per dm cube. So this is how we do that. Solubility now. Solubility of sodium triisocarbonate, which is our base, in moles per dm cube. So we are using this formula now. Use this formula. We have C1V1 equals C2V2. Remember what we are looking for now is C1. So C1 equals C2V2 divided by V1. C2V2 divided by V1. So permit me to quickly tell us our V1 is the first volume in centimeter cube. That is 150 centimeter cube. And then our C2 is what we are actually looking for. We are looking for our C1. Well, our C2 is given in the question 1. That is what we calculated previously to be the concentration of base in moles per dm cube. So our C2 now is 0.0344 moles per dm cube, and our V2 is the second volume in centimeter cube, which is 1000 centimeter cube. So if you are doing that now, okay, let me just quickly write that here. V1 is first volume in cm cube of dm cube. So we have it to be 150 centimeter cube, and then we have our C2 to be 0.0344 moles per dm cube. That was what we calculated. And then we have our V2 to be the second volume in cm cube of dm cube, and that is 1000 centimeter cube. So that is what we are making use of here. So we have our C1 to be our C2. From here we have 0.0344 times our V2, which is 1000. Our V2 is 1000 divided by the V1, which is 150 centimeter cube. 150 centimeter cube. So doing the calculation now, we are having 0.229333, and then to 3 significant figures now, because you must always leave your answer. It is very important that you know that your answer must be in 3 significant figures. So we'll be having it to be 0.0229 moles per dm cube. So that is the solubility. So solubility of the sodium triisocarbonate is 0.229 moles per dm cube. And then we move to the third question there. The third question is asking us for the mass of salt formed when 500 centimeter cube of B is completely neutralized by A. So the mass of salt formed now. Mass of salt formed when 500 centimeter cube of B is completely neutralized. Is completely neutralized by A. So that is what we want to look at now. So we are using this formula. This is the formula we are using. Mass of salt. Okay, mass of salt formed equals, we have CB, that's the concentration of base that we calculated earlier on, multiplied by the volume in dm cube, which is going to be 500 over 1000. You know, we are given 500 in the question. They said mass of salt formed when 500 centimeter cube is neutralized. So 500 centimeter, so we have it. Okay, let me just put it this way. Volume given in dm cube, multiplied by, we have the molar mass of sodium triisocarbonate. Molar mass of sodium triisocarbonate. So we have it to be looking like this: 0.0344 times 500 over 500 divided by 1000 multiplied by 142, which is the molar mass of sodium triisocarbonate. So from here now we are having 0.0344 times 500 divided by 1000 is going to give us 0.5 multiplied by 142, which is the molar mass of sodium triisocarbonate. From here now we are having all of that giving us 2.4424, and then to three significant figures, we are having it to become 2.44. So 2.44 grams is the mass of salt formed. Mass of salt formed equals 2.44 grams. That is that. And then the next question there, it said volume of carbon dioxide at STP that would be liberated from 1 dm cube of B. So we have that here. For now, volume of carbon dioxide at STP that would be liberated from 1 dm cube of B. That is what we want to look at now. So this is what we are using. We are going to use this formula, volume of carbon dioxide at, okay, let me put it this. Use this formula. We have volume of carbon dioxide at STP equals, we have Cb, that's the concentration of base in moles per dm cube, multiplied by the coefficient now, multiplied by the coefficient of the carbon dioxide, and then all multiplied by the volume given. Okay, let me put it this way: volume in dm cube, and then also multiplied by the molar mass of the gas. So that is what we'll be using. So we'll be looking at something that looks like this. We'll be having 0.03, okay, concentration of base now 0.0344 times the coefficient of the carbon dioxide is 1, multiplied by volume in 1 dm cube. We have 1 dm cube or 1000 centimeter cube, but since we are using dm cube, it is going to be 1, and then multiplied by 22.4. So when we do all of this, what we'll be having is going to be 0.77056, 0.0, we'll be having 0.77056, and then to three significant figures, we'll be having our volume now, volume of carbon dioxide to be 0. 0.771 dm cube. That is going to be the answer to this question. So that is that about question 2. Let us move now to question 3. Question 3 there is what we have on the screen right now. It says A is a solution of tetraoxosulfate 6 acid. B contains 1.8 grams of sodium triazocarbonate in 500 centimeter solution, 500 centimeter cube solution. Put A into the burette and titrate with 25 centimeter cube or 20 centimeter cube of B using methyl orange as an indicator. Tabulate your reading and calculate the average volume of acid used. So after calculating, we are assuming our average tetra value to be 21.4 centimeter cube. So these are the questions that are from this particular question. We have Roman numeral 1. There it says concentration. We should calculate the concentration of B in moles per dm cube. Roman numeral 2 says calculate the concentration of A in moles per dm cube. And 3 there says concentration of A in grams per dm cube. So that is what we want to look at right about now. So we have this. Question 3. Right. So what we are having, we are making use of 21 point, like you can see here, we are using 21.40 as our average tetra value. So let us quickly write out some of these information that we have there. So mass concentration of B, let's quickly do that first. Mass concentration of B in grams per dm cube will be, we have this, grams per dm cube multiplied by 1000. So since in the question we were given 1.8, if you look at the question here now, we're given 1.8 grams for the concentration of our B in 500 centimeter cube, but we want to take it to 1 centimeter, we want to take it to 1 dm cube, we want to take it to 1000 centimeter cube. That is why we are going to do this for now. So we are having 1.8, we are having 1.8 divided by 500 multiplied by 1000 over 1. So doing this now, we are having 3.6, and then 3.6 to 3 significant figures is going to give us 3.60 grams per dm cube. So we have that. Now let us go to answering questions. So we now have Roman numeral 1 now. Roman numeral 1, concentration of B in moles per dm cube. Concentration of B in moles per dm cube. So we are using this formula. Use this formula. Mass concentration, mass conc equals molar concentration times molar mass. So from here now we can calculate our molar conc. Molar concentration to be mass concentration divided by the molar mass. So we are having it looking like this: 3.60 divided by 106 rather. 3.60 divided by 106. So we are having it to look like this: 0.03396, sorry, 0.033962962. So to 3 significant figures now. To 3 significant figures, we are having our Cb to become 0.0340 moles per dm cube. Moles per dm cube. So that is our answer. This one here is our answer to that particular question. That is the concentration of our B in moles per dm cube. So let's go to the next question there. It says concentration of A in moles per dm cube, and then 3 it says concentration of A in grams per dm cube. So let's do that. 2 concentration of A in moles per dm cube. So we are having this here. Concentration of A in moles per dm cube. So we are using this formula. Use this formula. We have CAVA over CBVB equals NA over NB. So from this now, let's have our straight line equation. CAVA NB equals CBVB NA. Since we are looking for CA equals everything that we have here, CBVBNA, all divided by, we have it all divided by the coefficient of CA here, which is VANB. So from that, we'll be having our CB. We have calculated our CB previously to give us 0.0340 multiplied by our VB, that's the volume of our base, that's 25 centimeter cube, multiplied by the number of moles of acid, which is 1, all divided by, we have the volume of acid to be, from our question, we have it to be 21.40 multiplied by 1, which is the number of moles of base. So this is what we have here. So from here, we are having this. We have 0.85 divided by 21.40. So what we are having now is 0.039719. We have 0.03971996. So to 3 significant figures now. To 3 significant figures, we are having it looking this way: 0.0398. We have it to be 0.0398 mole. Okay, sorry, 397 rather. 0.23 significant figure is going to be 0.0397 moles per dm cube. So that is our answer for B. And then C, Roman numeral 3, the concentration of A in grams per dm cube. Concentration of A in grams per dm cube. So that is going to look like this. You are using this formula. Use this formula. We have mass concentration equals molar concentration times molar mass. So since we are looking for the concentration of A, we are using the mass conc equals molar concentration times the molar mass. And so we are having 0.0397 multiplied by the molar mass of our A, which is 98. So when we carry out that calculation, we'll be having 3.8906. And these to 3 significant figures now, always remember that, please. We'll be having it to be 3.89 grams per dm cube. So this is our final answer for this question: 3.89 grams per dm cube. So that is about that for question 3. Let us go straight to question 4. Let's see what question 4 has for us. This is question 4. Question 4 then says, A is a solution containing 0.0396 moles per dm cube tetraoxosulfate 6 acid, while B is a solution of impure sodium triisocarbonate acid containing 5.2 grams per dm cube of the solution. Put A into the burette and titrate with 25 cm cube or 20 cm cube of B using methyl orange as an indicator. Then tabulate your reading and calculate the average titra value. So the average volume of acid used for this particular question, we will be making use of this. We will be making use of 21.45. That's what we'll be using for the average titra value for this question, 21.45 centimeter cube. So the questions that we have there, we have to calculate the concentration of B in moles per dm cube. 2, we have to calculate the concentration of B in grams per dm cube. 3, we have to calculate the percentage purity of sodium triisocarbonate and then the percentage impurity of sodium triisocarbonate. So those are the questions that we have for us. 4 is what we are working on now. Question 4. So this is what we have. Let us quickly put down some of the informations from the question. We have our molar concentration of A to be 0.0396 moles per dm cube. And then from there also we have the mass concentration of impure sodium triisocarbonate. Mass concentration of impure sodium triisocarbonate. We have it to be 5.2 grams per dm cube. And we have said that we are using our average titra value, which is our volume of acid. Let me write it that way. Volume of acid used, we are using 21.45 centimeter cube. So let us now go into answering the questions. The question 1 there says we should calculate the concentration of B. Concentration of B in moles per dm cube. Concentration of B in moles per dm cube. So this is the formula we are using. Use this formula. We have CAVA over CBVB equals NA over NB. And then we have a straight line equation that looks like this. CAVA NB equals CBVBNA. The reason why I'm always writing this is because I want us to understand the processes. So we are looking for concentration of B now. So this is concentration of B here. We have concentration of B here. So that is what we are making subject of the formula. So we'll be having CB equals all that we have here, CA before the equal to sign, CAVANB, all divided by the coefficient of CB here, which is VBNA. So from that now we'll be having something that looks like this, 0.039. That is the concentration of our A, as you can see here, 0.0396 multiplied by the volume of our volume of our A, that is volume of acid used, is 21.45 multiplied by the number of moles of base is 1 from our equation, and it is all divided now, all divided by the volume of base is 25 centimeter cube multiplied by the number of moles of acid is 1. So we are having it looking like this. We have 0.84942 divided by 25. So what we are having there is giving us this we have 0.0339768. So when we do this to three significant figures, we're going to be having our CB now to be equal to 0.0340 moles per dm cube. That is going to be the final answer. 0.0340 moles per dm cube. So that is question 1. Let's go to question 2. Question 2 there is asking for the concentration of B in grams per dm cube. Concentration of B in grams per dm cube. Grams per dm cube. So we are using this formula. Mass concentration equals molar concentration times molar mass. That is what we are using. So since we have our molar concentration, we have our molar concentration to be 0.0, that is what we just calculated, 0.0340 multiplied by the molar mass of B, which is 106. So we are having it to be 3.604. So to three significant figures now, we are going to be having it to be 3.60 grams per dm cube. That is the final answer for that question. And then question 3. Question 3 there is asking for percentage purity of B. Percentage purity of B. So this is the formula that we are to use. Use this formula. Percentage purity equals, we have mass concentration of pure divided by the mass concentration of impure substance multiplied by 100/1. That is what we are going to be using. So looking at that now, we are having it looking like this. We have our mass concentration of pure to be 3.60, that's what we just calculated now, divided by the mass of impure as it was given in the question. If you look at this now, the mass of impure substance now, B is a solution of impure, we can see it here. B is a solution of impure sodium triethylcarbonate containing 5.2 grams. So that is the mass of the impure substance. So that is what we are having here, 5.2 multiplied by 100/1. So from here now, we will be having the calculation that is going to be giving us 69.230,769. So to three significant figures now, we'll be having percentage purity to give us 69.2%. That is going to be the percentage purity. So permit me to do the last question here. Let me just put the last question here. So we have Roman numeral 4 now. And that is talking about the percentage impurity. So remember that what we had from the question was just the amount of the impure substance. So now I want to see the percentage of the impure substance that is found in the whole of the substance. So percentage impurity equals 100 minus percentage purity. That is how we calculate that. So we are having it to be like this: 100 minus what we got for percentage purity just now is 69.2. So 100 minus 69.2, and that is giving us 30.8. So 30.8% is the percentage impurity in that particular salt, in that particular sodium triisocarbonate, which happens to be the base. So that is about the calculation for question number 4. So let us move to question number 5. Question number 5 says A is a solution of diabasic acid H2X. B is a solution containing 0.0340 moles per dm cube sodium triisocarbonate. Put A into the burette and titrate with 25 or 20 centimeter cube of B using methyl orange as an indicator, and then you tabulate your reading and calculate the average tetra value. So for this question, we'll be using this. We'll be assuming our average tetra value to be 21.60. The essence of using different tetra value is because I want us to be familiar with the system, so we don't get fixed to or fixated to a particular tetra value. We can get different tetra values from different questions, and then from our different practicals rather, and then when we have our tetra value, it will be easy for us to calculate or to carry out our calculations. That is the essence of using different average tetra values in all of the tutorial questions that you are working on. So for this question, we'll be making use of 21.60 centimeter cube as our average tetra value. So from that now, we are told to calculate these questions. So the equation for the reaction that we were given, H2X plus sodium triisocarbonate, giving us sodium X, we have Na2X plus carbon dioxide and water. So from the result that is provided and result and information provided above, calculate the A, or 1, concentration of A in moles per dm cube. 2, molar mass of A, given that solution A contained 3.9 grams per dm cube of the acid, and then Roman numeral 3 says value of X in H2X. So those are the questions that we have before us right now. So let us start with them. We are starting with number 1. Question 5. Right. So 1. Okay, before we go to that, the molar conc of B that we have, molar concentration of B, we have it to be 0.0340 moles per dm cube, and we have the volume of acid used to be 21.60 centimeter cube. So let us now go in. Concentration of A in moles per dm cube is what we want to start with. Concentration of A in moles per dm cube. That is where we want to start. So we are using this formula. Use this formula. CAVA over CBVB. Remember, I listed this formula as one of the formulas that you have to memorize in calculating questions as regards quantitative analysis. So it is very, very important you familiarize yourself with it. So over NaNB. From there, let's make a straight line equation. CAVA. I'm showing us all of these processes so we don't get confused. CAVANB equals CBVB NA. When we cross multiply, that is what happens. So this comes to this and this one goes to this. So what we are looking for now is the concentration of A. So we have Ca equals everything we have here, CBVB NA, all divided by the coefficient of Ca, which is VANB. From here now, we can have our CB as it is being given in the question. We have it to be 0.0340 times our VB, volume of base, is 25 centimeter cube. That is the size of our pipette. times the number of moles of acid, which is 1, all divided by, we have it all divided by the volume of the acid, which is 21.60, that is our assumed titre value, multiplied by the number of moles of base, which is also 1. So from here we are having this, we have 0.85 divided by, let me put it here, we have 0.85 divided by 21.60. So from here now we are having it to look like this. We have 0.0393518, and then these to three significant figures now. To three significant figures, we are having it to become 0.0394 moles per dm cube. That is our answer for this particular question. Concentration of A is 0.0394 moles per dm cube. So let us go to the next question to calculate the concentration of, to calculate the next question, which is the molar mass. We are asked to calculate the molar mass. You can see the question here. The molar mass of A, given that solution A contain 3.9 grams per dm cube of the acid. So that is what we want to calculate now. So from that we are having this, the molar mass of A, the molar mass of A, that is what we want to work on now. So we are using this formula for that. We are using this formula. Mass concentration equals the molar concentration times the molar mass. Mass conc equals the molar concentration times the molar mass. That is what we want to use. So since what we are looking for is the molar mass, so we make molar mass subject of the formula. So making molar mass the subject of the formula, molar mass subject of the formula. So molar mass now equals the molar concentration, equals mass concentration. Please permit me. We are making molar mass subject of the formula. So when we make molar mass subject of the formula, we'll be having this. Molar mass is made subject of the formula, so we'll be having mass concentration divided by the molar concentration. That is going to be the new formula. So we have mass concentration divided by the molar concentration. So from there we are having this, our mass concentration from the question, we have it to be 3.9. It was stated in the question there. We see it here. The molar mass, given that solution A contains 3.9 grams of the acid. So that is the mass concentration, and then divided by the molar concentration. Now we have the molar concentration to be 0.0, that was what we calculated previously, 0.0394. So doing the calculation, we'll be having it to become 98.94772. 98.94772. So these to three significant figures now. To three significant figures, we'll be having it to become 98.95. To three significant figures is going to be 98.9 grams per mole. So that is going to be the molar mass of A. And then the third question there, looking at the value of X in H2X. Let me just put that here. 3. Value of X in H2X. So the formula we are using, use this formula. We have H2X equals the molar mass of A. So H is 1 times 2 plus our X to give us the molar mass of A, which we just calculated to be 98.9. So we now have this one here. Okay, let me just rule here, so I will just complete that here. Just to end this particular question. So we have this one here to be 2 plus X equals 98.9. So coming here now, we have X equals 98.9 minus, because when this 2 here crosses equality sign to this other side here, it becomes minus. So we have 98.9 minus 2. So our X equals 96.9. So that is going to be the value of our X in that H2X. So the H2X there has 98.9. So the value of X in that H2X is 96.9. That is the answer to that question. So that brings us to the end of question 5. And then let us take the last question, which is question 6. Question 6 there says, A is a solution containing 0.0396 moles per dm cube of H₂SO₄, and B is a solution containing 3.6 grams per dm cube of H₂SO₄ salt. Put A into the burette and titrate with 25 cm cube or 20 cm cube of B using methyl orange as an indicator. Tabulate your burette reading and calculate the average volume of acid used. So from the results now, we have to calculate concentration of B in moles per dm cube, the molar mass of B, as well as the value of X in H₂SO₃. Similar question to what we just did. Now for this particular question, we will be assuming our average titre value to be 21.30. That is what we will be using for our average titre value, 21.30. So let us quickly do that as well. Question 6. Question 6. All right. So from the question now, we have the molar concentration of A. It was given in the question, the molar conc of A equals 0.0396 moles per dm cube. And then we have the mass concentration also. The mass concentration of B was also given in the question to be 3.6 grams per dm cube. So we are asked to calculate the concentration of B. That's the first question. Concentration of B in moles per dm cube. So the formula we are using CAVA over CBVB equals NA over NB. So straight line equation is giving us CAVANB equals CBVB NA. And then we are making CB here subject of the formula. So we have CB equals CAVANB divided by, we have the VB, that's the coefficient of CB now, VBNA. And so from that we are having all of this. Let's input all of our values. Our CA, concentration of A, is 0.0396 multiplied by the volume of acid used. From the question, we were told to use 21.30 multiplied by the number of moles of base, which is 1, all divided by the volume of base, which is 25, times the number of moles of acid. So from here we are having all of this to give us 0.84348 all divided by 25. All divided by 25. So from that we arrived at, when we did the calculation, we arrived at 0.0337392. 0.848, we have 0.84348 here divided by 25. So when we did that calculation, we are having 0.0337392. So to three significant figures now, we are now having it to become 0.0340. We have it to become 0.0340. That is what we have it to be. We can as well leave it at 0.0337, but let's leave it at 0.0340. So that is going to be the concentration of our B in moles per dm cube. That's our answer there. So let us go to calculate the next question. The next question asks us to calculate the molar mass of B. Molar mass of B. So we are using this formula. Mass concentration equals the molar concentration times molar mass times the molar mass. So since we are looking for the molar mass, so we'll be having mass conc, we'll be having the mass concentration divided by the molar concentration. So here we'll be having something that looks like this. 3.6. We're having 3.6, which is the mass concentration from the question. We have 3.6, then divided by the molar concentration. Molar concentration that we just calculated, we have it to be 0.0340. So when we do this calculation, what we'll be having is, we'll be having 106.24925. 106.24925. So these to three significant figures now. To 3SF, we'll be having 106 grams. Since it is three significant figures, we'll be having it to be 1.106 grams per mole. So that is the answer to this question. So that is the molar mass of B. And then the last question there asks us to calculate the value of X in H₂SO₃. Value of X in H₂SO₃. So let's use this formula. H₂SO₃ equals molar mass. So now we know that our carbon is 12, our oxygen is 16. We stated that in the commencement of this particular tutorial session. So let's go ahead now. Our X, we have it to be 2X plus our carbon is 12 plus our oxygen is 16 times 3. So we have 2X plus 12 plus 16 times 3 is giving us 48. It's giving us 48. Okay. all of these here equals our molar mass, which is 106. So here also we have it to be 106. So 2x now, 2x plus 12 plus 48 is giving us 60. 2x plus 60 equals 106. Now we want to make 2x subject of the formula. So 2x equals 106 minus, because when this 60 here crosses the equal sign to the other side, it becomes minus. So we have it to be 106 minus 60. So our 2x equals 106 minus 60 to give us 46. So x equals 46 divided by 2 to find our value for x. So it gives us 46 divided by 2. So our x equals 23. So that is the value of our x in H₂SO₃. So that brings us to the end of our tutorial questions or sample questions that we are using for our practical session in this particular titration aspect of the question. So I will plead with you to try as much as possible to go and practice questions. Use these questions, practice them, familiarize yourselves with questions, with formulas, and how to work them out when you see them in your questions. I encourage you to try as much as possible to like our content, share them with your friends, and if you are yet to subscribe, please don't fail to do so. Subscribe to our channel because it is going to be very, very beneficial to you. You can also find content on biology, on Greek on our channel, so please, I will plead with you and encourage you to try as much as possible to view all that is being done on this channel. Share them with your friends, let them also benefit from what you are getting. Thank you very much, and I wish you success in your exam. Bye for now.